We're going to go through and revisit this idea of translational equilibrium because we just have more forces to work with now that we have friction. So I told you we're going to work on a problem that has a block sitting on a table and there's friction between the table and the block, and maybe the whole table is inclined and we want to see what's going on. So here is a block. And it's sitting on a table. And the table is inclined, so we'll put a coefficient of static friction here of maybe 0.6 and kinetic friction of 0.4. We can give this block a mass of 5 kilograms, and let's incline this table. You know what? Let's have the incline of the table be our unknown, and we're going to say this. Two questions. We're going to find the angle that we need to get this block moving, or phrased a different way, find the maximum angle that we can incline this table to so that the block doesn't start moving. And then separately we're going to find the angle that we need to maintain a constant speed. This sounds like a good situation for a free body diagram. There is my ramp, incline, sorry. I'm going to have gravity going down. A normal force that points normal to the surface, and then I'm going to have a friction force. This thing wants to slide down, so I'm going to have a friction force that points up the ramp. All the motion is going to be along the ramp, so let's call that our positive x-axis. Perpendicular to the ramp can be our positive y-axis. Whole thing's got a mass of 5 kilograms. And anticipating that I'm going to want to move the screen to have more room, I'm just including the mass right on the top of that free body diagram. Here I go. I know that the angle inside my ramp here is an unknown. I have normal force that points in y, friction force that points in negative x, mg that points diagonally. So I'm going to have to break that into components. Okay, if that was the angle of my ramp, then there's my angle again. That makes this side mg cos theta, makes this side mg sine theta. And now I can start my equations. Sum of forces in x. I have an mg sine theta going down my ramp. I have fs going up the ramp. Together that's equal to mass times acceleration in x. I'm looking for that threshold value. Acceleration in x is going to be 0. I don't know the angle, that is the thing that I'm solving for, so I better put that in red just to try to remember. Fs, I'm looking for my threshold value. Fs max is going to be mu s times the normal force. The normal force I don't know. So y direction. My y forces, I've got a normal force going up, and I've got an mg cos theta going down. That's it. So it equals mass times acceleration in y. My acceleration in y had also better be 0. Alright, I have two equations with two unknowns. I'm going to have to do something with this. I'm going to take this equation and solve it for normal force equals and plug it in up here. When I do that, I get that my normal force is equal to mg cosine theta. I'm going to take that whole thing and plug it in there for normal force. So this top equation now reads mg sine theta minus mu static times mg cos theta equals 0. So I can separate that. Mg sine theta will be mu mg cosine theta. I want to get all the thetas together on one side, all the non-thetas on the other. Before I even do that, I'm going to cancel an m and a g. And that's interesting enough. That tells me that it doesn't matter what mass I put on this incline. If I put a 5 kilogram block or if I put a 150 kilogram block, I'm going to get the same answer. Solving for theta, I'm going to divide both sides by cos theta. I have sine theta over cosine theta. Sine over cosine, that sounds a whole lot like a tangent. So tangent theta on the left equals mu static on the right. And my angle is going to be the inverse tangent of mu static. My mu static on this one was 0.6. So I get the inverse tangent of 0.6, and my angle is 31 degrees. Second part of my question, once I'm moving, I want to find the angle needed to maintain a constant speed. There's a hint that this is in a video called Translational Equilibrium, Part 2. It is an equilibrium situation. If I'm going at a constant speed, what that tells me is that my acceleration is 0. So I'm going to redo this problem for once I'm moving. Here is how my free body diagram changes. I'm now looking at a kinetic friction, which has a different value. And where I had static friction, I now have kinetic friction. There's nothing that changes in x, except static becomes kinetic. There's nothing that changes in y. There's nothing that changes when I put it together. Really, the only thing that's changing comes right here. Instead of looking at a static case, I'm now looking at a kinetic case. So my angle, instead of being the inverse tangent of 0.6, is now the inverse tangent of 0.4, and that is about 22 degrees. It's less than what I had before, and that makes sense. It's always harder to get the thing moving than it is to keep it moving. So I have my ramp, it's sitting flat, or I have my board, I suppose. It's not a ramp yet. It's sitting flat. I lift up one side of it. I can keep lifting slowly. Once I hit 31 degrees, this thing starts moving, and then I have to lower it down to 22 degrees to keep it from speeding up. That's the whole process.